Hello, this is linear algebra. We're starting sections 1.1 and 1.2 today. These are introduction to vectors and linear combinations. Let's get started. All right. A vector in Rn is an ordered list of real numbers. The n in the superscript tells us how long the list is. And so when we say a vector in R3, it's a list of three real numbers. All right. So for example, these are all vectors in R2. The 2 here is indicative of the size of the vector. And so this vector has two numbers in it, -6 and 3. This vector has two numbers in it. They are allowed to be the same number. They don't have to be two different numbers. And the third vector has two numbers in them. These are given in the form of a formula that leads us to the number. Cosine of pi over 6 is the number square root of 3 over 2. And sine of pi over 6 is the number 1/2. But these are still numbers. So all of these are vectors in R2. This is a convention we use in our book. We're going to use bold letters to indicate a vector when we write them in print, and we will write vectors as a vertical list instead of a horizontal list. Some books do this differently, but this is the order that our book is going to do this. We say that -3 and 1 are the components of the vector. And so a vector in R2 is another way of saying that a vector has two components. All right. This graph, we have two vectors. The first vector goes from vector A to vector B. We call the starting point the tail of the vector and the ending point the head of the vector. That's because it's where the head of the arrow is on the head of the vector. So the head is the ending point, not the starting point. The tail is the ending point, is the starting point. And the way that we compute these coordinates is that we look at the trip that the vector v made going from the starting point to the ending point, and we split that trip up into its horizontal component and its vertical component. So to get from point A to point B, we have to travel 3 units horizontally to the left. So that's -3, and then 1 unit in the vertical direction, so that's +1. And so that's the vector -3 and 1. And then the other vector from P to Q, well, that vector is 4, 3. It's 4 units to the right, and then 3 units up to get from P to Q. What that means is that we can have two different vectors that have exactly the same components. This vector from J to K is -3 to the left and then 2 up. And then this vector from S to T is -3 to the left and 2 up also. They have exactly the same coordinates, so we say that the vectors are equal to each other. To be equal, they have to have the same components. They have to have the same horizontal displacement and the same vertical displacement. They do not have to be in the same location. They can be in different locations, and that's perfectly okay. All right. So if we have a vector in Rn, the magnitude of the vector. Magnitude is the same as the idea of the length of the vector. And we can calculate that vector using the Pythagorean theorem. We will take the individual components of the vector and square them. So v1 squared and v2 squared and v3 squared, however many components we have. Square them, add them all up together, and then take the square root of the total. So let's see an example of this. In this example, we have the vector down here that has the coordinates 4, 3. So that's 4 units to the right, 3 units up, and the 4 and the 3 are 2 legs of a right triangle. And therefore, the length of vector is the square root of 4 squared plus 3 squared, which is the square root of 16 plus 9, and that's equal to 5. So in this example, we're just looking at a 3, 4, 5 triangle. All right. There you go. We have 2 vectors that have the same number of components. That is, they're both in R2, or they're both in R3, or they're both in R4. We can add those 2 vectors by adding the entries in the corresponding positions of the vectors. When you see an example, you'll see this is completely easy, and I don't think anybody's going to have trouble with this operation here. So example here, I have a vector 3, 6, 1, and this vector is in R3. And this vector is also in R3. And so they have the same components. So we can add them by adding the first components together. 3 plus 2 is 5. And then we can add this next components together. 6 and negative 4 is 2. And then add the bottom components. 1 plus 3 is 4. And our final answer is 5, 2, 4. All right. Let's try another example here. In this example, we're going to add the 2 vectors 2, 3, and 4, 2, but we're going to use something called the head-to-tail rule. This is a visual way of adding the 2 vectors together. We're going to take these 2 vectors, 2, 3, which is vector v here. Why is it going? Why is it not writing here? Let's try that. There we go, v. And then 4, 2 is w. And we're going to position them end to end so that the head of v, that's the head on the arrow, so the head of v and the tail of w are exactly the same. And when we position them so that these 2 vectors meet end to end like so, then our combined vector v plus w that starts where v starts and ends where w ends is the combination of 2 units in the horizontal direction and then 4 more units in the horizontal direction and then 3 units in the vertical direction and then 2 more units in the vertical direction. And so v plus w is the vector 6, 5. So algebraically, we just add matching components. Visually, we position vectors head to tail. All right. Another operation we can do on vectors, we can multiply the entire vector by a constant. When we do this, every coordinate of the vector gets multiplied by that constant. So as an example, if I take the vector x and I multiply it by 6, then all of the components of x get multiplied by 6. So 2 gets multiplied by 6 and becomes 12. 1 times 6 is 6. Negative 3 times 6 is negative 18. And 8 times 6 is 48. I've taken the entire vector and stretched it out 6 times in every direction. All right. When we multiply a vector by a positive scalar, the vector gets larger or shorter in that direction, but it doesn't change directions. So if I take the vector v and I stretch it out by a factor of 3, I multiply it by 3 to get 3v. It's now 3 times longer, but it points in the same direction. The direction of the vector does not change. But when we multiply by negative scalar, like negative 2v, then the components they change sign. And so this vector that was originally 1, 1, this vector is now negative 2, negative 2. And therefore the direction has reversed. It's now pointing in the opposite direction. So scaling a vector can cause a direction to change, but only by exactly 180 degrees. It will flip exactly, to the opposite direction. That's the only direction change that can happen by multiplying by a scalar. All right. A unit vector, when we use the word unit here, we mean that the vector is exactly 1 unit long. So unit vector is 1 unit long. And if I have a vector that's not a unit vector, as long as it's not 0, because we can't divide by 0, but as long as it's not a 0 vector, we can turn it into a unit vector by finding the length of the vector, dividing by that length, and then scaling the vector by that amount. I'll show you an example here. In this example, the vector is negative 2, 4. That's 2 units to the left and 4 units up. And this vector crosses the unit circle at a point P. And the vector to point P, this blue vector, this is a unit vector. And we know it's a unit vector because it is the radius of a unit circle, and therefore it has to be exactly 1 unit long. And we would like to calculate that vector. So what we're going to do to find this unit vector is we calculate the magnitude of the original vector, negative 2 squared plus 4 squared. That's the two sides of this right triangle here. And when we square them, we get 20, take the square root. This side is square root of 20, which is a little less than 4.5. And so to make this into a unit vector, we need to scale this original vector by a factor of square root of 20. We need to make it smaller by this amount. And so we'll take the x coordinate and divide by negative 20, and the y coordinate and divide by negative 20, square root of 20, and the y coordinate and divide by square root of 20. And that gives us a unit vector that we want. And so this is this unit vector right here. Okay? Let's try another one. We will find a unit vector that is in the same direction as 4, 7, and negative 4. So the first thing we're going to do is going to find out how long is the vector v. That's the magnitude of V. And that magnitude is the square root of 4 squared plus 7 squared plus negative 4 squared. That's the square root of 16 plus 49 plus 16. That's the square root of 81, which is 9. All right. So the vector right now is 9 units long, and we want to make it just 1 unit long. And so we want to divide everything by 9 to make it smaller. And so the unit vector that we want, the vector u, is the vector 4/9 and 7/9 and negative 4/9. And that vector will be exactly 1 unit long. Okay? This is all summarized on this slide here. We calculate the magnitude of the vector, which is 9. Then we divide the vector by 9, or we multiply it by 1/9. That's the same thing. And that gives us a vector 4/9, 7/9, negative 4/9. This definition is going to be very important for the rest of this chapter. So I want to emphasize this topic. A linear combination of a set of vectors. So I have a group of vectors here. A linear combination of the vectors is a vector we could get by taking all of the vectors, scaling the vectors by some number, and then adding these vectors together. So it's a combination of adding the vectors together, but the vectors themselves can be multiplied by constants. The constants in the linear combination are called weights. So here's an example. This vector here, 13, 3, 19, is a linear combination of these other two vectors, because if I weight the first vector by a factor of negative 3, multiply it by negative 3, and I weight the second vector by a factor of 5, and then add them together, we get negative 3 times negative 1, negative 3 times 4, negative 3 times negative 8, plus 5 times 2, 5 times 3, 5 times negative 1, and 3 plus 10 is 13, negative 12 plus 15 is 3, and 24 plus negative 5 is negative 19. And so 13, 3, 19 is a linear combination of these vectors, because we can build 13, 3, 19 by taking multiples of these other two vectors and combining them together that way. This is not always possible. Here's an example of a vector that's not a linear combination. The vector 3, negative 7, 8 cannot be built using these three vectors, v1, v2, and v3. 2, 0, 9, 1, 0, negative 4, and 7, 0, 5. And the reason in this case is pretty obvious. As we go along, we'll come up with harder cases, but in all of these cases, the middle component is 0. So no matter how I weight them, when I add them together, the middle component will always be 0. There's no way that I can get a negative 7 for the middle component. And so if I have a set of vectors, sometimes there are some vectors that I can't build using those vectors. In this case, I can't build the vector 3, negative 7, 8 from the vectors that we have. Let's look at another example. 1, negative 7 is a linear combination of 1, negative 1, 4, 2, and 6, 0. Because if I use these weights, multiply the first vector by 3, multiply the second vector by negative 2, and multiply the third vector by 1, in other words, we leave that vector alone, then we end up getting 3, negative 3 for the first vector, negative 8 and negative 4 for the second vector. And since we're not multiplying this one by anything, it will still be 6, 0. And when we add these together, 3 and negative 8 is negative 5. Negative 5 plus 6 is 1. Negative 3 plus negative 4 is negative 7. Plus 0 is still negative 7. And that is vector v. So v is a linear combination of these three vectors. The weights that we need are 3 and negative 2 and positive 1. But we can also use this combination. If instead I weight this first vector by 1, this second vector by negative 3, and this third vector by 2, well, then what do we get? The first vector stays the same, so that's 1, negative 1. The second vector gets multiplied by negative 3 this time, so that's negative 12 and negative 6. And then the third vector gets multiplied by 2, so that's going to be positive 12 and 0. When we add those together, we get negative 12 and positive 12 cancel, so we just get 1. And then negative 1 and negative 6 is negative 7 plus 0. So that's also equal to v. And so this time we have a choice. We can use these weights, or we can use these weights, and they both give us the combination v. And so a linear combination may not be unique. There may be a choice in how we weight the vectors in order to get the result that we want. And just previewing some stuff that we're coming forward, from an engineering point of view, having a choice in the weights that we compute is an opportunity for engineers. It means that we can optimize for, maybe some particular value. We might find the choice that reduces the overall cost, or the choice that produces the minimal amount of waste, or the choice that produces the least amount of heat. So for whatever application we want, being able to identify that we have a choice in how we weight a linear combination gives us an opportunity to optimize the problem and to improve upon an existing solution by making better choices. All right, let's move on to the next slide here. So here we want to know, what are these linear combinations? These are drawn visually, so we don't have numbers to work with, but these dotted blue lines give me a combination that meets head to tail, where the first blue line and the second blue line meet at a corner, and they combine to give me the vector v. And if we look at this, the first blue dotted line is in the same direction as v1. So the direction is v1. but the blue line extends twice as far as the original V1. And so for this Earth's blue line, we're going to say that it's 2 times V1. And then the second blue dotted line is in the same direction as V2. It's parallel to V2, it's just up here. So the direction is V2, but it travels twice as far as the original vector V2. And so we're going to say that this piece is 2 times V2. And because they meet head to tail, we can add them together and say that V is 2V1 plus 2V2. Here's another example over here. Our first dotted blue line is in the direction of V1, but it travels 4 times as far as V1 does. So this is 4 times V1. The second blue line doesn't travel in the direction of V2 this time. It travels in the direction of V3, which is downwards, but it travels twice as far as V3 does. And so this is 2 times V3. And so the vector shown in this illustration is 4 times V1 plus 2 times V3. And so we can figure out what a linear combination is from a diagram or from just having the algebra, the numbers given to us. All right. We have a theorem here, and the math on this page is complicated, but I'm going to do an example in just a moment. If we have a set of vectors in Rn, and a vector that is a linear combination 2 different ways, that is, we have a choice of the weights that we can use. And so that there are 2 different sets of weights, and we can choose between these 2 sets. So this is one choice of weights. And then this is another choice of weights. So we have 2 choices of weights here. Then what we can do is we can combine them to create a third choice of weights. I can pick any real number t, multiply the first choice by t, and the second choices by 1 minus t, and add them together. And that will give us a brand new choice of weights. And because I can do this for any real number, then we have an infinite number of choices of weights. We found 2 of them, but we can actually expand that to an infinite number, which gives us even more possibilities as engineers. So let me show you an example of what I mean by this. In this example here, we have a vector 5, -1. And it is a linear combination of these 3 vectors, 3, 1, 1, -1, and 2, 2. And it's a linear combination in 2 different ways. In this example, the weights are 2, 1, and -1. And the second example, the weights are -1, 4, and 2. So what we're going to do now is we're going to find another linear combination, a brand new one that's not listed here. And our new linear combination will also add up to 5, -1. So what we're going to do this is we're going to start by picking any number we want to for t. For this example, I've chosen t equals 3, but you don't have to use 3. I'm just using 3 for this example. When we choose t equals 3, then we multiply all of the weights in the linear combination by 3. So 2 becomes 6, 1 becomes 3, and -1 becomes -3. So I'm multiplying the combination by the number I chose. For the second linear combination, I don't get to choose another number. For the second linear combination, the second number is always 1 minus t. So if t is 3, 1 minus 3 is -2. And that means I'm going to multiply the second linear combination by -2. So -1 times -2 becomes +2. 4 times -2 becomes -8. And 2 times -2 becomes -4. And now I'm going to add these two linear combinations together. 6 and 2 become 8. 3 and -8 becomes -5. And -3 and -4 becomes -7. And if we did this right, this combination is not either of the two that were given to us. It's a new linear combination, but it also creates 5, -1. So let's try this. In the top row, we're going to get 24 minus 5 minus 14. And the bottom row, we're going to get 8. -5 times -1 is +5. And -7 times 2 is -14. So in the top row, we have 24 minus 5 is 19. 19 minus 14 is 5. In the bottom row, 8 plus 5 is 13. But 13 minus 14 is -1. And so that checks. We took two existing linear combinations and we engineered a third one that also works. And because I can choose a different starting number every time I do this process, I can create an infinite set of linear combinations, which gives me even more power to optimize linear combinations if I want to do something. Okay? All right. In R2, we're going to define two special vectors here. The first vector is called E1, which is 1, 0, and the second vector is called E2, which is 0, 1. In physics classes, you may have heard these called I and J, and I will sometimes slip up and call them I and J myself, but our book calls them E1 and E2, so that when we go into higher coordinates, we have a pattern we can follow. In R3, we're going to find three vectors. E1 is 1 unit in the first direction, E2 is 1 unit in the second direction, and E3 is 1 unit in the third direction. We call these the standard basis vectors. We will extend this definition if we need to, so that if we're in R15, we have 15 standard basis vectors. They'll be numbered E1 all the way down to E15. The advantage of standard basis vectors is that computing linear combinations is very, very simple with something we can do in our head. I'll do a couple of examples, and then we're about to wrap up. So if I want to compute the vector that is equal to 5v1 and minus 6e2 and plus 2e3, I'm going to write this out. But you'll see how easy this is. You don't have to write this out. This is E1, and then minus 6, and then this is E2, and then plus 2, and then this is E3. E3 is 1 unit in the third direction. And so when we multiply this together, in the top row, we get 5 times 1, plus negative 6 times 0, plus 2 times 0 is just 5. In the middle row, we get 5 times 0, minus 6 times 1, plus 2 times 0. And then our bottom row, we get 5 times 0, minus 6 times 0, and 2 times 1. And so the components just turn out to be the same as the weights, 5 and negative 6 and 2. The standard basis vectors just let me take the weights and write them directly into a vector and not really have to do any calculations. We can do the calculations, which is what I did here, but after a while you just say that's 5, negative 6, 2. So if we wanted to go the other direction and we have this vector and we want to write it as a linear combination of E1 and E2, well, that's 4 times the vector in the first direction and negative 2 times the vector in the second direction. 4 times E1 and negative 2 times E2. And that's how this linear combination, these standard basis vectors work. All right, that's it for today. I will have another video for the next section, and I look forward to seeing you again soon. Take care.